Hello. I'd like you to take a look at these four different expressions. Notice any similarities here? All right, go ahead and using the tools you know how to multiply polynomials, go ahead and simplify all four. All right, I hope you pause the video. Here we go. 5x times 5x 25x squared. 5x times 7 then 7 times 5x then 7 times 7. Right? I really hope you did not get 25x squared plus 49. These two middle terms are a big part of our answer. Now you notice that they're exactly the same. Right? What did we multiply here? 5 times x times 7, 5 times x times 7. The commutative property tells me that this product must be the same as this product. 7 times 5x, 7 times 5x. So I have 35x plus another 35x like terms. I'm multiplying 35 times x for both of them. So x are my units here. 35 plus 35 is 70. Instead of 35 plus 35, I could just say double 35, you get 70. And then the 49 is there. And the 25x squared is there. Now that doubling is even more clear for this example. X times x is x squared. X times 1. That's negative here, so that's negative x. X times 1, that's negative here. And 1 times 1 is 1. Negative times negative is positive here. Right? So I've got negative 1 times x, negative 1 times x. I don't even know which one is which. Doesn't really matter. Right? I'm doing negative 1 times x twice. So if I double 1, I get 2 plus 1. And if I make that minus a little bit longer, I can convince you it's x squared minus 2x plus 1. Maybe I should make that a little more clear and erase my negative sign so that it is very clearly a minus sign. And my 2 looks kind of big there. I might make you think of a coefficient 2. Try to improve my handwriting. X squared minus 2x plus 1. And that process will happen every time we're multiplying in a similar fashion. If I have some binomial being multiplied by the exact same binomial, well, I get a times a times b, it's just ab, then b times a, well, b times a is ba, but we like to put our variables in alphabetical order, so I'll put that as ab, and then b times b, which is the definition of b squared here, right? Whatever your a and b are, you're going to have a times b and its commutative property reversal, b times a. It's the same thing. If you add a number to itself, whatever that quantity is, adding it to itself 2 times, you have 2 of them. Come on, pen. There you go. You have 2 of them. And the b squared is there. And the a squared is there. So if we back up just a little bit, we can simplify in a different way. Anything times itself, we call that thing squared. Right? Now, I said simplify in a different way. Technically, this is not simplified. This blue version looks a lot nicer than the black version, right? It takes up less space. It's very clear that I have the same factor twice because that's what squared means. Here, you might not have even noticed right away that this was the same binomial twice in a row. But this is not simplified because we still have parentheses. This is considered simplified. This is fully factored, right? Factor means to write as a product. So here it's factored, and here it's factored even more nicely. Remember prime factorization. I think our example was 400. Right? 2 and 2 and 2 and 2 and 5 and 5. Instead of writing all 4 2's, we just say we have 4 2's. Instead of writing both 5's, I just say I have 2 5's here, right? So that's a little nicer looking than that. Same way, this is looking a little bit nicer than this. Both are factored. Both of these are factored. It's still the prime factorization. But this is nicer. This is nicer. This, come on. This is simplified. So our formula is anytime you have a binomial times itself, you're multiplying the a times a, you get a squared. You are multiplying the b times b, you're getting b squared. But you also multiply the a times b twice. So we get ab twice. Now, as for the name of this, if we take a number like 400, and we recognize that 400 is 20 times 20, instead of 4 times 100, I could have said 2 times 10, 2 times 10 here, right? Here's our 2 times 10, 2 times 10. Because I can write 400 as a number times itself, I call 400 a perfect square. So here's a polynomial that I could write as something squared, right? 400 equals something squared. Here's something written as something squared, so it's a perfect square. But to emphasize that we're talking about polynomials here, not just natural numbers, we call this a perfect square trinomial. This is a perfect square trinomial. This is a perfect square trinomial. Why? Because it's equal to 5x plus 7 times itself. Right? Perfect square trinomial, because it equals a polynomial times itself, a binomial times itself. All right, now we can look at our second pair here. Let's switch colors. Again, starting from scratch, 5x times 5x, 25x squared. So far, it looks pretty much the same. 5x times 7. 5 times 7 is 35. Then negative 7 times 5, x. 7 times 5 is 35. Notice, though, this was 5 times 7, positive 5 times positive 7, positive 35. Over here I have a positive 5 times a negative 7. So that's going to give me a negative 35. And then finishing up the 7 times 7, except this 7 is negative. So it's 7 times 7, negative 49. So I still have 25x squared, just like with this version. I kind of have 49, but instead of a positive 49, now I'm getting a negative 49. And in the middle, 35 plus 35 is 70, but I don't have 35 plus 35. I have 35 minus 35, opposite signs here. Any number minus itself is 0. I have 0x. Right? Someone gave me 35 rubies, and then someone else stole those 35 rubies. How much money do I have left? Nothing. I don't need to know how much a ruby costs. I don't have any. This is my final answer. I'm not going to write plus 0x, because 0 times x is 0. I'm not going to write plus 0. 0 is the additive identity. So even though this looks like it should be a trinomial, just like these, just like this one, I get those two middle terms combining to get some middle term. Here we go. These two middle terms add up to 0, and so that cancels out. Same thing here. X times x is x squared minus x plus x minus 1. Well, these are opposites of each other, minus 1. That's my whole answer. Right? We can see that in general. A times a, there's my x squared. B times negative b. But in between, I have the a times negative b. I have the a times positive b. And whatever a and b are, their sum, because they're going in opposite directions, is going to be 0. Not the sum of a and b, the sum of the product of a and b and the opposite of the product of a and b. So I get a squared minus b squared. So our two formulas kind of look like the reverse of each other. For a perfect square trinomial, I'm getting a nice, compact, easy to read, easy to write, something being squared. But the simplified version is now taking up more space. I have 3 terms now, but no parentheses. With this expression, I start out with parentheses and a whole bunch of terms here, 4 terms written out with some duplicates. But once I multiply, because these middle terms dropped out, instead of 2 terms, it simplifies, instead of 3 terms, it simplifies to only these 2. So this is our simplified version. And this is not a perfect square trinomial because it's not equal to something times itself. Right? If I look at, let's say, 22 times 18, let's actually pick different numbers here. Let's say 72 times 68. That might take you a little while. But we can recognize 72 is 70 plus 2. 68 is 70 minus 2. 70 times 70, 7 times 7 is 49, times 10 times 10. 2 times 2 is 4. So we get 4,896. Not quite in my head. I had to write some things down. But the arithmetic I was doing in my head, that's still a lot faster than 72, 68. 8 times 2 is 16. 56 plus 1 is 57. 6 times 2 is 12. 42 plus 1 is 43. 6, 7, 8, 9. 5, 6, 7, 8. 4. 4896, 4896. Now, you're not going to be multiplying numbers that are the same distance above and below an easy number very often. Right? This is almost a bit of a parlor trick. It's convenient if you can recognize it, to use that kind of shortcut. But when we're dealing with expressions, recognizing, hey, this is the same binomial except one's plus the other's minus, I can jump straight to here. 25x squared minus 49. Done. Right? Here's the square of my first terms. Here's the square of my second terms, but a minus because I need a positive times a negative in order for these two terms to be positive and negative. Right? That's why we call this expression, it's not a perfect square, it's a difference, subtraction, of a perfect square and another perfect square. So we call it difference of squares. So those are two special polynomials that you encounter very frequently, and it can be a big time saver. Instead of multiplying the regular way, we can just 5 times 5, 25x squared. 5 times 7, 35, double that, 70. Done. 7 squared, 49. Done. Right, we can jump straight to here pretty easily and quickly. Now it's going to be even more important once we start factoring. Once we start going the other direction, working from this trinomial back to its factored form takes some doing. And you can learn how. It's not impossible. It's definitely doable. But we have to think, we have to try. There's a lot of guess and check involved. Or you can do it a really long way without guess and check, but I don't like that way. It takes a really long time. But if we can recognize, oh, wait a minute, that's a perfect square, that's a perfect square, that's 7 squared, that's 5x squared, 5 and 7 is 35, that's double 35, done. Okay, that's a perfect square, that's a perfect square, I'm finding their difference, I know it's going to work out. 5x, 7. One's positive, the other's negative. Notice it doesn't matter if the first one's negative, the second's positive, or the first one's plus, the other one's minus. As long as they're opposite signs there, we're all good. Right? So practice recognizing and using those special formulas, whether it's difference of squares or perfect square trinomial. And of course, continue to practice your regular multiplying, however complicated those expressions are. Okay.